So here we talk about the p-adic absolute values, and as an example, we talk about what is stem-adic of 98. So the next question is that I'm going to talk about what is called non-Archimedean property. And the reason that why we talk about what is called non-Archimedean property is because when you think about our theorem, that our theorem states that for every non-trivial absolute values, it's either equivalent to the p-adic one or it's either equivalent to a real one. So there must be, some conditions or properties that can divide our theorem into two cases. And this property is what we call the non-Archimedean property. So absolute values is called non-Archimedean if it satisfies these inequalities here for any x and y. And this is sometimes called strong triangle inequality because you can see that this inequality can imply triangle inequality just straightforward. And otherwise, it is called Archimedean. So this should be everything that we need for this theorem. For every non-trivial absolute values, we talk about non-trivial, we talk about absolute values. On the rational numbers, it's either equivalent to the real one or it's equivalent to the p-adic one. And you can think about like this classifies all the absolute values over the rational numbers. So over the rational numbers, you give any absolute values, and you would say, okay, you either equivalent to the p-adic one or otherwise you're equivalent to the real one. So this is the theorem here. And now we try to think about how do we formalize the theorem in Lin. So give me a sec. So firstly, let's have a look like how do we define absolute values? How do we create absolute values in Lin? So I call it my absolute values, and you're given ring. R to be a ring. So you can see that the difference that between here and the definition on the slides. We define it over a field on the slide, but we actually can define over a ring because we don't actually need to define over a field here. And for any f is from this ring to real numbers, and this is just the what it looks like in the math level of Lin. It's called multiplicative ring norm, and if you put your mouse on that, you can see that a multiplicative norm on a ring is a multiplicative ring semi-norm, such that fx is equal to 0 implies x equals 0. So the following things here is that the first line here is telling Lin, okay, I'm using f to be the function, to be our rational absolute value, and you can see there are several stories along here. It's Lin asking you, okay, tell me that can you prove this following these axioms. So if I open one of them, you can see the second line is Lin asking you, okay, can you prove f0 is 0 or 0 is standard to 0? And also it's like the next line is asking you, okay, for any RS in your ring, can you prove it satisfies this triangle inequalities here? But we can't actually fill in these stories, actually, because the f that we are given here is very random, and it doesn't really have any particular properties. So this is just as an example. We actually can prove some of them here. If you think about how do we define the usual real absolute values on the rational numbers, so we just take the positive part. So the first line is telling okay, I'm using the real absolute values that you defined in the math lab before, and then the following axioms is just the same thing as above. So for example, the third line, which is about triangle inequalities, and you can actually prove this just by using the knowledge that you had before. And there is a upper arrow here just because Lin is thinking about r plus s to be a real numbers. So we say that r and s are two rational numbers. But when you are taking the function, the real absolute values, Lin is saying, okay, give me some real numbers. But we know that rational numbers can, they are real numbers automatically. So Lin just saying, okay, let's recognize this R plus S to be the real numbers. So there's an up arrow here, and same as the on the right-hand side. And thirdly, is the p-adic norm. And fortunately, that the p-adic norm has been defined in the math lab, so we don't actually need to do some further works here. But the things that we need to do is to make it to be our absolute values, or what is called multiplicative ring norm. So we still have to prove some axioms here, but they are all easy to prove because I'm pretty sure that they have when they define the p-adic norm in the math lab, they have proved this as well. So these are all done in our group work. And next is about how do we define the equivalence relation here. And so equivalence says that, so you give me a ring and you give two multiple ring norm, F and G, and they exist a positive real number such that one is the power of the other one. This is not the final version that we got in our work, because when we think about some ring here, we should think about, okay, whether we need these properties of ring or we need anything, something else. But just to make it easier to explain, I use the ring here. And this is actually an equivalence relation, and you can prove this by doing some simple exercise. You prove this is reflexive, you prove this is symmetric, and you prove this is transitive. So for example, for the reflexive, you say that F is an absolute values, and you want to show that F is equivalent to itself. So let's make an example of Lin. Let's open technical for this. So okay, there's an arrow here. So in Lin, here is your what are you focus on? Is your goal. So R is a ring, F is an absolute values. You want to show F is equivalent to itself. So it means that so firstly, we can tell Lin that what do you mean by my equivalence? So we can write some simple code here. So Lin will say, okay, my equivalence means that there exists a positive real number such that fx to the power of c is equal to fx. And that should be clear that we should use 1. So we can just tell Lin that we use 1. Lin will say, okay, and now you need to show that 0 is strictly less than 1, which is very trivial here. And also fx to the power of 1 is fx. Then everything here should be very easy to solve. And also, if you think about symmetric and transitivity, you can all do them very quickly. So next is how do we define the non-Archimedean properties here? So we say that non-Archimedean property for any R and S, F R plus S is less or equal to the maximum of them. And you might think it is a little bit strange, or it is a little bit different than what from what we talk about in our slides. It's because when you look at this definition, there's no actually there's nothing about absolute values. So, and the reason here is that we don't actually need to care about whether we define non-Archimedean property over the rational absolute values or not. So we just need a function f, and function f is from alpha to beta. And now we think about, okay, if we want to make this to be true, what properties that we need? So the first thing is that we need to add elements in alpha because we have R plus S. So that's why we have has add. If you delete has add, Lin will tell you that I can't do that because I don't know whether we can add elements in alpha. And similarly, we need beta to be the linear order. So I actually forgot what is meant by linear order, so I can put my mouse on this. So a linear order is a reflexive, transitive, antisymmetric, and total relation. And the reason that we use linear order here because there is a smaller or equal than symbol here. So this is my the non-Archimedean property. So this is basically that we talk about in our slides how we formalize these definitions in Lin. Some of them has been added into MathLab, and some of them is going to be added into MathLab. So let's try to go through the proof for this theorem. So we say that there are actually two conditions. The first one is f is, your norm or your absolute values is non-Archimedean, and the other one is not Archimedean, not non-Archimedean, or you say Archimedean. So let's try to go through the non-Archimedean first. And the result is that if your norm is non-Archimedean, then it is equivalent to the p-adic one. So there exists some prime numbers p, and your absolute values is equivalent to the p-adic absolute value. And the first thing that I'm going to show is that if your norm is non-Archimedean, then it is bounded on integers. And it's suffice to consider, we can prove it is bounded on naturals because fx is equal to f minus x. So we can just prove things on naturals. And if you think any natural numbers n, we can actually write n as the sum of 1, which is 1 plus 1 plus 1 plus 1 plus 1. And then by the non-Archimedean property, it is less than some of them or one of them, but they are all 1, so it is less or equal than norm of 1. And you can easily prove the norm of 1 is 1. So it is bounded on naturals, so it is bounded on integers. So this is first lemma that we need. And secondly, we want to consider that there exists, if f is non-Archimedean and f is non-trivial, then there exists prime numbers such that it is strictly less than 1. So we know by the non-Archimedean property, they all smaller or equal than 1. But now we want to think about, okay, I want to show that there exists at least one prime number such that it is strictly less than 1. Otherwise, if for any prime numbers, it is equal to 1, then by the prime factorization, everything will be set to 1 except 0, which means that f is trivial. But our hypothesis tell you that f is non-trivial, then this could be done as well. So why do we need to consider whether there exists prime numbers is strictly less than 1? Is that we are considering this set on the next definition, alpha. So now we are considering this kind of, set contains all of the integers such that the norm of that is strictly less than 1. And this is actually forms an ideal. And you can, and to make it to be ideal, you need to fill in these stories. Lin is asking you, okay, tell me that how do you prove that this forms an ideal by doing these 3 stories? And so we know this forms an ideal, and this ideal actually contains the span of P, which is Pz. And this is true because P is already in your ideal. So this is true as well. And we know that Pz is what we call the maximum ideal. So it is maximum, and this alpha contains this ideal as well. So which means that these two are the same by proving that your alpha is proper. So here is the lemma we need, is that this alpha, so everything that is strictly less than 1 is actually equal to the span of P. So you give any numbers that has norm strictly less than 1, it is in the form of some P times Z, and Z is some integers. And this is quite important because now if you consider any integers A, you can factorize A respect to P. The P is the number that you found in the above. And we can factorize A. It's like we write A times A is equal to B times B to P to the power of M, and P doesn't divide B. So if P doesn't divide B, which means that B is not in the ideal that we defined above, it's because, I mean, if the ideal defined above is the span of P, but P doesn't divide B. So B is not in the ideal that we defined above, which means that the norm of B is equal to 1. Because we think about everything straight less than 1. If B is not in that ideal, then the norm of B is equal to 1. So now we think about the norm of A. So the norm of A is actually equal to the norm of P to the power of m, because the norm of B is equal to 1. And then everything should be done, which is to the p-adic 1 to the power of s, where s is defined like this, minus log the norm of P over log P. And you can easily check this is actually true here. So this lemma, my valuation equal, is actually telling you that for any integers, the norm of A is equal to p-adic 1 to the power of s, where s is defined something like this. So, but in our theorem, we state that for every rational numbers, but this could be extended to rational numbers very easily just by thinking about if you take the norm of P over Q, it's equal to the norm of P over norm of Q, and then everything should be extended as well. So the non-Archimedean case is done. So this lemma states that if f is non-Archimedean and f is non-trivial, then there exists a prime number P such that it is equivalent to the p-adic 1. So this is basically everything about non-Archimedean case. And the things left is the Archimedean. So for the Archimedean, I mean, the first lemma, I mean, if it is non-Archimedean, then if and only if it is bounded on natural, it's just a remark. You may think about, I mean, we just talk about one direction above, but actually the other direction should follow very easily here. So we just think about this. And so now we think about if it's Archimedean. So we know it is not, if it is not Archimedean, then everything should be bounded by 1. So if it's Archimedean, then there exists at least one natural numbers. The norm of 1, the norm of n is strictly larger than 1. So we can say we just take the minimum of such a number, which has norm strictly larger than 1. And that's how do we define it to, I mean, in Lin, we say that a naught to be the smallest number that we find in HF. So if you click on find, it states that if P is a predicate on naturals and HP is a proof, then net find HP is the smallest natural number satisfying P. So we don't actually need to write write other codes here. And so we know that this is actually should be strictly larger than 1 for the unknown, because if it is 1 or it is 0, then it is not true because f0 is equal to 0 and f1 is equal to 1. And we want to say that it is strictly larger than 1. So we can prove that this is actually larger than 1 for the unknown. And now we try to think about what we did for the non-Archimedean case, and this should be very similar. It's like we define some alpha to be log the norm of a naught over log a naught, and you can actually prove this is larger than 0 just by thinking about a naught is larger than 1, and also f a naught is larger than 1. So by the properties of log, this is larger than 0. And the key lemmas that we solve in the Archimedean case are basically divided into 2 parts. So we want to prove that for any natural numbers, the norm of n is equal to n to the power of alpha. And if you think that is true, then the Archimedean case is done, because just by following the same process for the non-Archimedean case. So we want to prove that this is actually equal. So we divided that into 2 cases, which is called lemma 1, lemma 2. I mean, there are some repetition here, but we won't call it in the math lab, I mean, later. So these are basically 2 lemmas, and I'm going to talk about later. And if this 2 is true, then we know that it is equal. Then by the same process for the non-Archimedean, then for if f is Archimedean, then it is equivalent to the real one, and this is basically done. And the lastly is the whole theorem. Whole theorem here. If f is absolute values and f is non-trivial, then if it is either equivalent to the real one or there is some prime numbers, it is equivalent to the p-adic one. And 1, 2, 3, 4, 5, 6, 7, and a few lines just solve this theorem. But I mean, we actually need everything that we talked about above. So this is how do we formalize the Ostrowski theorem in the lim part. And if we go back to PowerPoint. So the lemmas left here is that we want to prove for any natural numbers, the norm of n is less or equal to n to the power of alpha, and the other side as well. And actually, the proof for these two lemmas are basically very similar and using the same process. So we just go through lemma 1 here. So by the definition of alpha, we know that the norm of n naught is equal to the n naught to the power of alpha. If you look back, what is alpha? Alpha is log the norm of n naught over log n naught. So you just do some simple calculations. You can find this is basically true. And we know n naught is the smallest number that it is straightly positive. It's straightly larger than 1. Then this is true as well. And not to the power of alpha is larger than 1. So now we can try to think about how do we write n in terms of n naught. So by using basis representation theorem, we can write n is equal to a0 plus a1 n naught and plus dot dot dot. And for any ai, which is between 0 and n naught. So by the choice of this, we can simply observe that the norm for any ai is less or equal to 1, because n naught is the smallest number that the norm of that is really positive, really larger than 1. So if this is less than n naught, then it means that the norm of them are less or equal to 1. So now we can think about the norm of n. So the norm of n is it's less or equal than this by using the triangle inequality. And the second line, just by using the axiom 2 in our definition of absolute values. And now we can say, because the norm of n naught is equal to n naught to the power of alpha, so we substitute it back. And we know that for everything, for every ai, the norm of ai is less or equal to 1. So it is less or equal to 1 plus this. And then we can factorize, to take n naught to the power of s alpha, and to think about what happens if that goes to infinity. So it is less or equal than this thing goes to infinity. And it is actually a geometric series here. Then by using the result of that, we can say it is equal to n naught to the power alpha over n naught to the power alpha minus 1. And we say we should see here, which is a constant. So, a lot of inequalities and relations here. But the result that we gave is that for any naturals n, the norm of n is less or equal than c to the power of n, c times n to the power of alpha for some constant c. Now we can use some sequence of limits here by taking smaller n and big n from natural numbers, and just taking the square roots on both sides, and we get this relation, which is the norm of n is less or equal than some square root c, c to the power of n times n to the power alpha. And by letting n big n to the infinity, we can say that the norm of n is less or equal than n to the power alpha, because the first part, c to the power of n, when n goes to infinity, this goes to 1. So now the proof is basically following from this result. And this is lemma 1 and lemma 2. I mean, the other direction just basically does the same thing here. So I will go through the same process. So this is basically that what we did for this theorem. And firstly, we divide into 2 cases, and we talk about what happens for each case. And actually, this theorem, I mean, we also consider this theorem on what we call the rational function field. So rational function field, you can think about it's like you take 2 polynomials P and Q, and you think about what is P over Q. And this forms a field which is called rational function field. And this theorem basically does a very similar thing on these fields as well. And we are currently still working on rational function field. So, I mean, maybe later I can have another chance. Somewhere I can talk about rational function field as well. And this theorem also, I mean, does much more things than I think or we think here. Is that this theorem applied on rational numbers, absolutely, and also it also applied on extension of rational numbers. So this should be another very big result here. So this is my just presentation for this theorem and how we did for Lim. And we are still working on filling some small stories, and hopefully I will get it done as soon as possible. So thank you very much.